For thousands of years, humanity looked toward the stars believing the universe was filled only with light. Yet hidden among those brilliant lights were places where even light itself could never escape. Imagine a region of space so powerful that every passing object disappears forever. No fire, no signal, no spacecraft, and not even the fastest thing in existence can find a way out. That fastest traveler is light itself. Racing through the universe at nearly 300,000 kilometers every second, light seems unstoppable. Yet black holes can imprison even this cosmic messenger. At first, the very idea sounds impossible. How can something invisible capture light, the one thing that defines everything we are able to see throughout the universe? The answer lies within gravity, but not the kind we experience every day. Black holes reveal gravity pushed to its absolute limit, where the familiar rules of nature begin to transform. Every step closer to a black hole brings stranger discoveries. Time slows, space bends, and reality itself begins to behave in ways that challenge everything we believe about the universe. For centuries, these mysterious objects existed only as mathematical predictions. No telescope had ever seen one, and many scientists doubted they could truly exist in nature. Some believed black holes were nothing more than strange equations with no physical meaning. Others suspected the universe might be hiding something far more extraordinary than anyone imagined. As telescopes improved and technology advanced, tiny clues began appearing across the night sky. Invisible giants seemed to influence stars without revealing themselves directly. Stars suddenly changed direction. Clouds of glowing gas accelerated to incredible speeds. Entire regions of space behaved as though an unseen monster was lurking nearby. Astronomers could not ignore these mysterious observations. Something invisible was shaping the motion of nearby matter with astonishing power, yet it remained completely hidden from view. The mystery deepened with every new discovery. The more scientists observed the universe, the stronger the evidence became that these invisible objects were real. Then came an astonishing realization. Black holes are not rare cosmic accidents. They may exist by the millions throughout our galaxy alone. Even more surprising, nearly every large galaxy appears to hide a supermassive black hole at its center, quietly influencing billions of surrounding stars. Our own Milky Way is no exception. At its very heart lies an invisible giant whose mass is millions of times greater than our Sun. Although we cannot see this enormous object directly, we can watch nearby stars racing around something hidden, as though orbiting an invisible sun. These observations reveal one of science's greatest strengths. We do not always need to see an object directly to know it exists. Sometimes its influence tells the entire story. Black holes are no longer science fiction. They have become essential pieces of modern astronomy, helping scientists explain some of the universe's most powerful and mysterious events. Yet one breathtaking question still remains. If nothing can escape a black hole, not even light, what truly happens beyond its invisible boundary? To answer that question, we must travel back in time to discover how an impossible idea slowly evolved into one of the greatest scientific discoveries in human history. Long before anyone spoke of black holes, scientists believed gravity was powerful, yet they never imagined it could imprison light itself. The very thought seemed to defy common sense. In the 17th century, Sir Isaac Newton described gravity as a force acting between masses. His laws explained falling apples, orbiting planets, and countless motions throughout the universe. Newton's theory was so successful that it became the foundation of physics for generations. Few questioned whether gravity might behave differently under more extreme conditions. At the same time, scientists were still debating the true nature of light. Some believed it consisted of tiny particles, while others argued it behaved as waves spreading through space. If light were made of particles, one curious question naturally followed. Could gravity pull on those particles just as it pulls on everything else in the universe? In 1783, an English scientist named John Michell proposed a remarkable idea. He imagined a star so massive that its gravity would prevent even light from escaping into space. According to his calculations, such an object would remain completely invisible. It could still exist, but no light would ever leave its surface to reveal its presence. The idea was astonishing, yet it attracted little attention. At the time, no one possessed the technology needed to test such an extraordinary prediction. Years later, the French mathematician Pierre-Simon Laplace reached a similar conclusion. He also suggested that nature might contain invisible stars, hidden by overwhelming gravity. These mysterious objects became known as dark stars. Although they resembled the modern idea of black holes, scientists still lacked the knowledge to understand how they might truly exist. As the 19th century progressed, new discoveries about light changed everything. Experiments showed that light behaved as electromagnetic waves rather than ordinary particles. This breakthrough created uncertainty. If light was a wave instead of a particle, would gravity still affect it? The old idea of dark stars gradually faded from scientific discussion. For decades, the concept remained little more than a forgotten curiosity buried within old scientific papers. Few researchers believed it held the key to one of nature's greatest mysteries. Then, in the early 20th century, a young physicist named Albert Einstein completely transformed humanity's understanding of gravity, space, and time. Einstein proposed that gravity was not simply a force pulling objects together. Instead, massive bodies curved the fabric of space-time itself, changing the paths that objects followed. Suddenly, the old concept of invisible stars returned with astonishing new meaning. If space-time could bend enough, perhaps light itself could become trapped forever. Every star in the universe is born with a limited supply of fuel. No matter how brilliant or massive it may seem, every star is slowly moving toward the end of its remarkable life. For millions or even billions of years, a star shines because an incredible battle is taking place deep within its core. Two powerful forces continuously struggle against one another. Gravity pulls every particle inward, trying to crush the star beneath its own enormous weight. At the same time, nuclear fusion pushes outward with extraordinary energy. This delicate balance allows a star to remain stable for ages. As long as enough fuel remains inside its core, neither force can completely overpower the other. Deep within the star, hydrogen atoms collide under immense pressure and temperature. They fuse together to form helium, releasing vast amounts of energy in the process. That energy slowly travels outward through countless layers before escaping into space as the light and warmth that illuminate entire solar systems. Our own sun has maintained this balance for nearly 5 billion years. Every sunrise on Earth is powered by nuclear reactions taking place deep inside its blazing core. Yet even the sun cannot shine forever. One day, its hydrogen supply will begin to run low, forcing the ancient balance between gravity and fusion to change forever. As fuel disappears, the outward pressure weakens. Gravity immediately senses the difference and begins squeezing the star inward with increasing strength. The star responds by heating its core to even higher temperatures, allowing new forms of nuclear fusion to begin. For a time, the struggle continues once again. Massive stars experience this cycle repeatedly. They create heavier and heavier elements, transforming hydrogen into helium, helium into carbon, and eventually producing iron. Iron marks a dramatic turning point in a star's life. Unlike earlier reactions, fusing iron consumes energy instead of releasing it, bringing the star dangerously close to collapse. With no new source of energy strong enough to resist gravity, the star begins losing the battle it has fought since the day it was born. In only a matter of seconds, the enormous core collapses inward at incredible speed. Material that once took millions of years to build suddenly crashes toward the center. Temperatures soar into the billions of degrees. Pressures become almost unimaginable, exceeding anything humanity could ever reproduce on Earth. The collapsing star can no longer support its own weight. Gravity gains complete control, crushing matter into densities beyond ordinary human comprehension. The outer layers rebound in a spectacular explosion known as a supernova, briefly outshining entire galaxies and scattering newly formed elements across the cosmos. Those scattered elements eventually become the building blocks of future stars, planets, and even life itself. Every atom of iron in your blood was forged inside an ancient, dying star. But while the outer layers race into space, something extraordinary is happening deep inside the collapsing core, something far more mysterious than the explosion itself. If the remaining core is massive enough, gravity refuses to stop. The collapse continues without mercy, leading to the birth of one of the most extraordinary objects in the universe, a black hole.
The moment a massive star exhausts its final source of energy, gravity is no longer opposed by any force powerful enough to hold it back. The collapse becomes sudden, unstoppable, and unimaginably violent. Every second, billions upon billions of tons of matter rush toward the dying star's center. The core shrinks at incredible speed, becoming smaller, hotter, and denser with every passing moment. What was once a giant star, millions of kilometers across, now begins collapsing into an object only a tiny fraction of its original size. Yet almost all of its mass remains. As the core contracts, gravity grows dramatically stronger. The smaller the collapsing object becomes, the more intensely it bends the surrounding fabric of space-time. Pressure rises beyond anything found inside ordinary stars. Atoms are crushed together, their familiar structures destroyed under conditions that challenge everything we know about matter. Electrons are forced into atomic nuclei, combining with protons to create neutrons. In an instant, ordinary matter begins transforming into something far more extreme. If the remaining core is relatively small, the collapse eventually stops, leaving behind an incredibly dense neutron star only a few kilometers across. But if the core contains enough mass, even neutron matter cannot resist gravity forever. The crushing force continues growing without mercy. At this point, no known force in nature is capable of stopping the collapse. Gravity overwhelms everything, pulling the remaining matter inward without limit. The core shrinks beyond imagination. Mountains of matter become the size of cities, then smaller than islands, then smaller than entire countries. As space-time bends more deeply, the escape speed continues increasing. Eventually, it reaches an extraordinary milestone, the speed of light itself. Once that happens, a boundary forms around the collapsing object. Beyond this invisible surface, nothing can escape, regardless of how powerful or fast it may be. This boundary is known as the event horizon. It is not a physical wall or solid surface, but it marks the point of no return. Anything crossing the event horizon is forever separated from the outside universe. Every possible path now leads only deeper into the black hole. From far away, the black hole appears perfectly dark because no light can climb back across the event horizon to reach distant observers. Ironically, black holes are often surrounded by some of the brightest regions in the universe. Matter falling inward becomes superheated, glowing brilliantly before disappearing forever. Powerful jets of energy can erupt from the area surrounding a black hole, stretching for thousands of light years and shining brighter than entire galaxies. Every black hole possesses an invisible boundary unlike anything else in the universe. It cannot be seen, touched, or crossed twice. Astronomers call this mysterious border the event horizon. The event horizon is often misunderstood as a solid surface, but it is nothing of the sort. It is simply the point where escape becomes forever impossible. Imagine standing beside an enormous waterfall. Far upstream, you can still swim against the current, but beyond a certain point, no amount of strength can carry you back. A black hole behaves in a surprisingly similar way. Outside the event horizon, escape remains possible. Cross that invisible boundary, and every path leads only inward. The escape speed grows stronger the closer you approach the black hole. At the event horizon, that required speed finally reaches the speed of light itself. Since nothing in the universe can travel faster than light, nothing crossing the event horizon can ever return. The universe itself closes every possible escape route. To someone falling toward the black hole, nothing special appears to happen at first. There is no visible wall, no sudden impact, and no flashing warning signs. The traveler simply continues drifting forward, completely unaware of the invisible boundary that has already sealed their fate forever. But to a distant observer watching safely from space, the same event appears completely different. Time itself begins playing a remarkable trick. As the traveler approaches the event horizon, their movements appear slower and slower. Every second seems to stretch longer than the one before. Their clock appears to tick more slowly, their signals arrive farther apart, and their motions gradually become almost frozen against the darkness. Eventually, the traveler seems to stop completely at the edge of the black hole. Their light grows dimmer, redder, and weaker until it finally disappears. This strange illusion is caused by the extreme warping of space-time. Gravity stretches time so dramatically that distant observers witness an entirely different reality. Yet from the traveler's own perspective, nothing freezes at all. Their watch continues ticking normally as they cross the event horizon without noticing anything unusual. This extraordinary difference reminds us of one of Einstein's greatest discoveries. Time is not absolute. It depends on where you are and how gravity shapes space-time around you. Everything the traveler hoped to communicate with the outside universe is now trapped forever. Even radio waves and beams of light cannot climb back across the horizon. Beyond this point, every future moment leads deeper toward the mysterious center of the black hole. Returning is no longer a matter of technology, but a violation of nature itself. The event horizon is more than a boundary. It separates two completely different regions of reality, one still connected to the universe we know, and one forever hidden from observation. Scientists can calculate exactly where the event horizon should exist, yet no telescope can reveal what truly lies beyond it. The greatest mystery begins precisely where every visible clue comes to an end. Beyond that invisible curtain waits the most mysterious destination in all of physics, a place known as the singularity, where our current understanding of the universe may completely break down. Beyond the event horizon lies a destination unlike anything else in the known universe. It is a place no telescope can observe, no spacecraft can explore, and no signal can ever escape. Scientists call this mysterious destination the singularity. It represents the point where matter is crushed to unimaginable density, and our current understanding of physics begins to fail. According to Einstein's equations, gravity continues compressing matter without stopping. The collapsing core becomes smaller and smaller until its density appears to approach infinity. Infinity is not simply an unimaginably large number. In physics, it often signals that a theory has reached the edge of its ability to describe reality accurately. This does not necessarily mean that nature truly contains infinite density. Instead, it may mean that our mathematical tools are no longer complete. Imagine using a map designed for a small town to navigate an entire planet. The map is not wrong, it simply was never intended for such an enormous challenge. In much the same way, Einstein's theory works brilliantly across the universe. Yet inside a singularity, gravity becomes so extreme that another theory may also be required. That missing piece is believed to involve quantum mechanics, the branch of physics that governs the smallest particles and the strange rules of the microscopic world. Unfortunately, relativity and quantum mechanics describe reality in very different ways. Each succeeds within its own domain, yet combining them remains one of science's greatest challenges. Deep inside a singularity, both theories should operate together. Yet when physicists try to unite them mathematically, the equations refuse to cooperate. Some researchers believe that space and time themselves may no longer exist in the forms we recognize. The familiar concepts of distance and duration could lose all meaning. Others suggest that matter never reaches infinite density at all. Instead, unknown quantum effects might halt the collapse before a true singularity can form. Several modern theories even propose that the center of a black hole could contain entirely new structures, hidden from the outside universe by the event horizon. Ideas such as quantum gravity, loop quantum gravity, and string theory attempt to describe these mysterious conditions, but none has yet been confirmed experimentally. Because no information can escape the event horizon, scientists cannot observe the singularity directly. Every conclusion must be built from mathematics, indirect evidence, and careful reasoning. This makes black holes the ultimate natural laboratories. They push every known law of physics to its absolute limit, revealing where our understanding begins to break apart. The singularity is not merely a mystery hidden inside black holes. It may also hold clues to the birth of the universe itself during the first moments after the Big Bang. For many years, scientists believed black holes formed only from the deaths of massive stars. Then astronomers uncovered something even more astonishing: black holes far larger than anyone had imagined. These enormous objects are known as supermassive black holes. Unlike their smaller cousins, they contain millions or even billions of times the mass of our sun. No one knows exactly how these cosmic giants first appeared. Their origins remain one of the greatest unsolved mysteries in modern astronomy. Some scientists believe they grew slowly by swallowing gas, dust, and nearby stars over billions of years. Others think they were born surprisingly large during the universe's earliest moments. Wherever astronomers looked, they kept finding the same extraordinary pattern. Nearly every large galaxy seemed to hide one of these invisible giants at its very center. This discovery raised an obvious question. Was it merely a coincidence, or did these hidden monsters play a vital role in shaping entire galaxies? Our own Milky Way contains one of these mysterious objects. Hidden deep within its crowded center lies a supermassive black hole known as Sagittarius A. Although Sagittarius A cannot be seen directly, astronomers have spent decades watching nearby stars racing around an invisible object with tremendous gravitational power. Some of those stars complete enormous orbits in only a few years, reaching speeds of millions of kilometers per hour as they swing around the hidden giant. By carefully tracking these stellar motions, scientists calculated the mass of the unseen object. The result was astonishing. Nearly 4 million suns compressed into an invisible region. Only a supermassive black hole could explain such extraordinary behavior. No known cluster of ordinary stars could remain packed together so tightly without quickly falling apart. These giants do far more than simply sit at the centers of galaxies. Their gravity influences enormous regions of space, helping shape the evolution of entire galactic systems. As gas and dust spiral toward the black hole, they form a rapidly spinning disk called an accretion disk, where temperatures rise to millions of degrees. This swirling material shines so brightly that it can outshine every star within the surrounding galaxy, producing one of the most luminous objects in the universe. Some supermassive black holes also launch gigantic jets of charged particles, traveling close to the speed of light, stretching across hundreds of thousands of light years. These powerful jets can influence the birth of new stars by heating or dispersing enormous clouds of gas throughout their galaxies. Far from being simple cosmic destroyers, supermassive black holes may actually help regulate the life cycles of galaxies, balancing creation and destruction across cosmic time. In 2022, astronomers revealed the first direct image of Sagittarius A, offering humanity its first glimpse of the invisible giant hidden at the heart of our own galaxy. That remarkable image confirmed decades of observations and provided yet another powerful victory for Einstein's theory of general relativity. The universe is filled with invisible giants silently shaping galaxies across billions of light years. Yet an even greater mystery remained. How could scientists ever photograph something that emits no light at all? For generations, black holes were considered impossible to photograph. After all, they emit no light of their own, making them completely invisible against the darkness of space. The challenge seemed almost hopeless. Telescopes collect light, but a black hole allows no light to escape. How can you photograph something that cannot be seen? The answer came from looking not at the black hole itself, but at everything happening around it. Its surroundings reveal a story that the black hole cannot hide. As gas, dust, and broken stars spiral toward a black hole, they form a rapidly spinning accretion disk. Friction heats this material until it glows brighter than millions of stars. Before crossing the event horizon, the superheated matter releases enormous amounts of energy, producing brilliant light across radio waves, X-rays, and other forms of radiation. Although the black hole remains perfectly dark, the glowing material surrounding it creates a bright ring that outlines the invisible boundary hidden within. Einstein's theory predicted that the black hole's immense gravity would bend light itself, distorting the glowing ring into a shape unlike anything found elsewhere in the universe. Capturing such an image, however, required technology beyond any single telescope ever built. The target was simply too small and unimaginably far away. The supermassive black hole in galaxy M87 lies about 55 million light-years from Earth. From our planet, it appears no larger than a tiny orange resting on the moon. No existing telescope possessed enough resolution to observe such a distant object directly. Scientists needed a completely different approach. Instead of constructing one enormous telescope, researchers connected radio observatories spread across the entire Earth, allowing them to work together as a single giant instrument. This worldwide network became known as the Event Horizon Telescope. Observatories from multiple continents synchronized their observations with extraordinary precision. Each telescope recorded enormous amounts of data onto specialized storage systems. The information was so vast that it could not be sent through the internet. Instead, hundreds of hard drives were physically transported to powerful computing centers, where scientists carefully combined the observations collected from every telescope. Months of processing transformed those scattered signals into a single extraordinary image. For the first time in history, humanity had glimpsed the shadow of a black hole. In April 2019, the historic image was revealed to the world. A glowing orange ring surrounded a perfectly dark center, matching Einstein's predictions with astonishing accuracy. The picture quickly became one of the most famous scientific images ever produced. It represented decades of international cooperation and years of technological innovation. 3 years later, astronomers achieved another milestone by revealing the first image of Sagittarius A, the supermassive black hole at the center of our own Milky Way. These remarkable photographs did not show the black holes themselves. They revealed the shadow cast against the brilliant light of the surrounding accretion disk. Humanity had finally accomplished what once seemed impossible. We had photographed the invisible, proving once again that curiosity, patience, and science can illuminate even the darkest corners of the universe. For much of history, black holes were thought to be silent objects drifting alone through space. Then astronomers discovered that some of them travel through the universe in pairs. These black hole pairs orbit one another for millions or even billions of years. With every orbit, they move a little closer together, locked in an endless gravitational dance. As they circle faster and faster, something extraordinary happens. They begin releasing energy, not as light or heat, but as ripples traveling through the very fabric of space-time. Einstein predicted these ripples in 1916. He called them gravitational waves, tiny distortions that spread across the universe at exactly the speed of light. Imagine dropping a stone into a perfectly still lake. Waves spread outward in every direction, carrying energy across the water long after the splash has disappeared. Gravitational waves behave in a remarkably similar way. Instead of moving through water, they travel through space-time itself, gently stretching and squeezing everything they pass. These waves are unimaginably small. By the time they reach Earth, they change distances by less than the width of a single proton, making them incredibly difficult to detect. For decades, many scientists doubted they could ever be measured. The signals seemed far too weak, hidden beneath countless sources of noise and vibration. Yet engineers refuse to give up. They designed one of the most sensitive scientific instruments ever built, capable of measuring changes smaller than anything previously imagined. This remarkable observatory became known as LIGO, the Laser Interferometer Gravitational Wave Observatory, with giant detectors built thousands of kilometers apart. Each detector sends powerful laser beams through long vacuum tunnels. The light reflects from perfectly polished mirrors before returning to a central measuring point. If a gravitational wave passes through Earth, space-time itself stretches in one direction while shrinking in another, changing the distance traveled by the laser beams. The difference is incredibly tiny, but sophisticated instruments can measure it with astonishing precision, revealing the passage of a gravitational wave. On September 14, 2015, something extraordinary happened. Both LIGO detectors recorded the same faint signal within a fraction of a second. Scientists spent months verifying every possible explanation. After exhaustive analysis, only one conclusion remained. Two black holes had collided over 1 billion light-years away. During the final moments before their collision, the black holes orbited each other hundreds of times every second, releasing unimaginable amounts of energy. In less than a single second, they converted several suns' worth of mass directly into gravitational waves, briefly producing more power than all the stars in the observable universe combined. More importantly, the detection confirmed one of Einstein's greatest predictions almost exactly 100 years after he first described gravitational waves. Humanity had gained an entirely new way of observing the cosmos. Instead of only seeing the universe through light, we could now listen to its deepest vibrations. Black holes have fascinated scientists for decades, but they have also inspired one unforgettable question. What would actually happen if a human being traveled toward one? The answer depends on one important detail: the size of the black hole. Surprisingly, not all black holes would affect a traveler in exactly the same way. A small, stellar black hole possesses an incredibly strong gravitational pull over a very short distance. Gravity changes so rapidly that the human body would experience extreme tidal forces. Imagine your feet being pulled much more strongly than your head. Every part of your body would accelerate at a different rate as you approach the black hole. This difference in gravity would stretch your body farther and farther until it resembled a long strand of spaghetti, a process scientists humorously call spaghettification. Although the name sounds amusing, the reality would be anything but. The tidal forces would eventually become so overwhelming that no known material could withstand them. Long before reaching the event horizon of a small black hole, these immense forces would tear apart spacecraft, equipment, and every atom of the unfortunate traveler. Supermassive black holes, however, tell a surprisingly different story. Because they are vastly larger, gravity changes much more gradually near the event horizon. A traveler falling toward a supermassive black hole might cross the event horizon without immediately noticing anything unusual or experiencing destructive tidal forces. From the traveler's perspective, the journey could appear calm. Their heartbeat, breathing, and watch would all continue normally as they drifted beyond the point of no return. Meanwhile, observers watching safely from far away would witness a completely different event. They would see the traveler moving slower and slower as the black hole's gravity stretched time. Eventually, the traveler would appear almost frozen near the event horizon, becoming dimmer and redder until finally disappearing from view altogether. Neither perspective is wrong. Einstein's theory allows both observations to exist simultaneously because time itself flows differently under intense gravity. Could the traveler send one final message back to Earth after crossing the event horizon? According to everything we currently understand, the answer is no. Every radio signal, every beam of light, and every attempt at communication would remain trapped forever inside the black hole along with the traveler. Some physicists have imagined extraordinary possibilities beyond the event horizon, including wormholes leading to distant regions of space, or perhaps even entirely different universes. These fascinating ideas appear in many books and films, but no scientific evidence has yet confirmed that such passages actually exist in nature. Another mystery known as the information paradox asks whether information falling into a black hole is destroyed forever or somehow preserved in ways we do not yet understand. This puzzle has challenged the world's greatest physicists for decades and continues inspiring new theories about quantum gravity and the fundamental nature of reality. Black holes are more than cosmic traps. They are natural laboratories where the limits of space, time, gravity, and human knowledge are tested more severely than anywhere else in the universe. The closer we come to understanding these extraordinary objects, the more they remind us that the greatest discoveries often begin with the courage to ask questions that seem impossible to answer. After centuries of discovery, black holes remain among the most mysterious objects ever found. Every answer they provide seems to uncover an even deeper question waiting beyond it. They have changed the way we think about gravity, space, and time. What once seemed impossible has become an essential part of modern astronomy and physics. Yet the greatest mystery is not how black holes form. It is what truly happens after matter disappears beyond the event horizon, where no information can return. According to Einstein's theory, everything crossing the event horizon continues falling toward the singularity. But quantum physics tells a far more complicated story. One of the biggest puzzles is known as the black hole information paradox. It asks a simple question with extraordinary consequences. Can information ever be destroyed? In quantum mechanics, information should never disappear completely. Every particle carries information about its physical state, and the laws of nature seem to preserve it forever. Black holes appear to violate that principle. If everything falling inside is lost forever, then information may vanish from the universe, something quantum physics refuses to accept. This contradiction has challenged physicists for nearly 50 years. Solving it may require an entirely new understanding of reality itself. Another remarkable discovery added even more mystery. In 1974, Stephen Hawking proposed that black holes are not completely black after all. According to Hawking's calculations, tiny quantum effects near the event horizon allow black holes to slowly release energy into space. This phenomenon became known as Hawking radiation. Over unimaginable spans of time, it suggests that black holes may gradually lose mass and eventually disappear completely. But if a black hole evaporates, what happens to everything that once fell inside it? Does the information escape, remain hidden forever, or disappear completely? No one knows the answer with certainty. Some theories suggest the information is encoded within Hawking radiation, while others propose entirely different explanations. Ideas such as the holographic principle, quantum gravity, and space-time emergence attempt to solve this extraordinary puzzle, but none has yet been proven. Black holes have become more than astronomical objects. They are now testing grounds for the deepest ideas in mathematics, relativity, and quantum physics. Every new telescope, every gravitational wave detection, and every computer simulation brings scientists one step closer to understanding these cosmic mysteries. Future observatories may reveal details that today's instruments cannot detect. The next great breakthrough could arrive from a signal traveling across billions of light years. Perhaps one day humanity will discover a theory capable of uniting Einstein's relativity with quantum mechanics, finally explaining what truly happens inside a black hole. Until that moment arrives, black holes remain silent guardians of the universe's greatest secrets, reminding us that the cosmos is still far more mysterious than we can imagine. The story of black holes is not the end of our journey through the universe. It is an invitation to keep exploring, keep questioning, and keep searching for answers hidden among the stars.